Okay, so in this video here, we're going to talk about the inverse trigonometric functions. Our objectives is to understand and use the inverse sine function, understand and use the inverse cosine function, understand and use the inverse tangent function, and then find exact values of composite functions with inverse trigonometric functions. All right, we'll begin with the inverse sine function. So here you can see the graph of y equal to sine of x. And as you probably noticed before, the sine function is not a one-to-one function. In fact, here I'm using a horizontal line just to show you that it intersects the horizontal line in multiple places, right? And in fact, an infinite number of places. And so therefore it's not a one-to-one function and does not have an inverse. However, if we restrict the domain of our sine function to the region between negative pi over 2 to pi over 2, we have a function now that is one-to-one. Okay, so if we basically ignore the rest of the trig function and just look in the area between negative pi over 2 to pi over 2, we get a nice one-to-one function. And we could define the inverse of it. And so the inverse sine function, written as sine inverse of x, sometimes also written as arc sine of x, is the inverse of the sine function on its restricted domain negative pi over 2 less than or equal to x, x less than or equal to pi over 2. The function is defined as y equal to sine negative x, gives the angle y such that sine of y equals x. And from the graph of the y equal to sine function that we restricted the domain of sine to negative pi over 2, right, to pi over 2, and that was the domain for sine. And then of course the range of sine is negative 1 to 1. And so you can see that when you, as we've learned probably before, when you talk about inverse function, the domain and range swap. Okay, and so you can see that the domain of the inverse function is between negative 1 and 1, and the range is between negative pi over 2 to pi over 2. Okay, so let's go ahead and take a look at this the graph of the sine inverse function. And so here I'm going to go ahead and type sine inverse of x. And you can see this is the red graph that you see here. And that's the sine inverse function. How does it compare to the y equal to sine of x? Well, that's sine of x, and you can see that, of course, sine is not a one-to-one function and continues on forever. But when you restrict it from pi over 2, negative pi over 2 to pi over 2, you get the corresponding inverse function. And so we could restrict the domain here from negative pi over 2 to pi over 2. And you can see that the graphs are going to run symmetric to the line y equal to x. In fact, let me change this color. Oops. See if I could change this color to say maybe a black and dotted color, and then maybe 1.5 there. Okay. And so let's go ahead and say, if we zoom in just a tad, you can see that any point that's on the graph of sine, xy, there's going to be a corresponding point at the other, when you swap the y and x. You can see they're symmetric. Let's go back to the notes. Okay, so then let's see how we can find exact values of sine inverse. So the way you can do this is follow this scheme here. You let theta equal to sine inverse of x, and then rewrite this as a theta sine inverse of x as sine theta equal to x, where negative pi over 2 is less than or equal to theta, and theta is less than or equal to pi over 2. Use the exact values in the table to find the value of theta in the interval of negative pi over 2. So that should be a negative pi over 2 to pi over 2, such that sine of theta equals x. And so here we have some common angles, or special common angles, multiples of pi over 6 and pi over 4 here, that fall in the interval from negative pi over 2 to pi over 2. Okay, so these are the corresponding points. We could use this as an 8, or you could use the circle for that matter. All right, suppose we're asked to evaluate sine inverse of 1/2. Sine inverse of 1/2. And so we would say theta is equal to sine inverse of 1/2. So we would rewrite this as sine of theta equal to 1/2, and then use the table by first identifying where 1/2 is, and then we see that it's here, so that means it corresponds to the angle pi over 6. And so that means theta is equal to pi over 6, and therefore sine inverse of 1/2 is pi over 6. Likewise, you could do the similar thing here in the next example, where we're asked to calculate sine inverse of sine inverse of negative root 2 over 2. And so we could rewrite theta. We could say theta is equal to sine of negative root 2 over 2, and then rewrite that as sine of theta equals negative root 2 over 2. And then once again, we could go here to the table and find our negative root 2 over 2 and see it corresponds to negative pi over 4. Okay, so we see that theta equals negative pi over 4. Therefore, sine inverse of negative root 2 over 2 is equal to negative pi over 4. Okay, so that's how you find exact values of sine inverse. Calculators also can be used. Most scientific calculators have a sine inverse function as well. Might not write it as a nice pretty fraction like this, but it most likely will give you some kind of decimal approximation of the answer. All right, let's go on to the next function, cosine inverse cosine function. So likewise, if we consider the graph of cosine, we can see it too is not a one-to-one function. However, if we restrict the domain of the sine function to 0 to pi, then the function would become a one-to-one function. And so likewise, once again, you could see the graph is not one-to-one function since it doesn't pass the horizontal line test. And so once again, we could restrict it between 0 and pi. So we get this portion here. And on this portion here, we could see it's a nice one-to-one function. Okay, in other words, what we're doing is basically ignoring the graph that any x values to the left of 0 and any x values to the right of pi. And we just get this portion right here. Okay, so we focus on that portion there, and then we could define the cosine inverse function as the following. The inverse cosine function, written as cosine inverse of x, or arc cosine of x, is the inverse of the cosine function on its restricted domain between 0 and pi. The function is defined as y equal to cosine inverse of x, gives the angle y such that cosine of y equals x. Once again, just like cosine has a domain, we restricted the domain to 0 to pi, and then of course the range was -1 to 1. We could see for the cosine inverse function, these guys are going to swap, and you see that the domain is -1 less than or equal to x, and x less than or equal to 1, and the range is 0 less than or equal to theta. Here I meant to say y less than or equal to pi. Okay, so let's go ahead and take a look at the inverse function. All right, so here we're using decimals again. We'll say y equal to cosine inverse of x, and you can see it looks a lot different than the similar. I mean, I guess it's kind of similar to the sine function, the sine inverse function, but in a different position, if you could see here. Okay, and so putting this along with cosine of x, we can see there is the function cosine. Let's change the color there and let's make it a little bit different here. Let's make it blue. Okay, all right, so you can see, but we did restrict it between 0 and pi. Okay. And you can see the symmetry once again along the line y equal to x. And let's go ahead and change that color to dotted line, make it 1.5. Thank you. And maybe make it black. Okay, so you can see that the line, so the blue line is the cosine function restricted on the domain from 0 to pi. Therefore, an inverse function has domain -1 to 1, right? -1 to 1, and its values, or its y values, are going to fall between 0 and pi. Okay. Once again, the symmetry with respect to the line y equal to x. If you have a point on the graph on one, then swap the coordinates, you have that same point at the other part of the graph. Okay, so let's go back to the notes. All right, finding the exact values of cosine inverse of x. Let theta equal cosine inverse of x. Rewrite theta equal to cosine inverse of x as cosine of theta equal to x, where theta falls between 0 and pi. And then we could use the exact values in the table to find the value of theta in the interval from 0 to pi. Here's another typo here. That's supposed to be 0 and pi, such that sine of theta equals x. All right, once again, using special angles that fall between 0 and pi, we could use that to help us evaluate or find exact values of, say, cosine inverse of -1/2. All right, first step is to rewrite or let theta equal cosine inverse of -1/2, which tells us, if you rewrite this, this is cosine of theta equal to -1/2. Right, so then finding in our table where we have cosine of theta equal to -1/2, which is here, that shows that it corresponds to the angle 2 pi over 3. So then we have theta equal to 2 pi over 3. Therefore, cosine inverse of -1/2 is 2 pi over 3. All right, let's try another example here. So we're asked to calculate cosine inverse of 1/2. So we have theta equal to, or let theta equal to cosine inverse of 1/2, and then rewrite this as cosine of theta equal to 1/2. Then we could use the table here to identify where 1/2 is for the output, and then see that it corresponds to pi over 3 there. All right, so then we see that theta equals pi over 3, which tells us then for cosine inverse is, cosine inverse of 1/2 is pi over 3. All right, let's look at the next inverse function, the inverse tangent function. So in the same way we determine an inverse function for sine and cosine, we can restrict the domain of tangent. Okay, so we could do the similar thing here, and once again, tangent basically looks like that all throughout, right? And it has these asymptotes, and so what we're going to do is restrict the domain of tangent to be from -pi over 2 to pi over 2, and then we could focus on just this portion of the graph. And there you can see it's a 1-to-1 function, and we could see if we do that, then we'd restrict the domain. We restrict the domain to open parenthesis negative pi over 2 to pi over 2 because it has asymptotes at negative pi over 2 and pi over 2. And we know the range is going to be from negative infinity to infinity. And so let's define the inverse tangent function. So the inverse tangent function, written as tangent inverse of x or arctangent of x, is defined for all real numbers. The function is defined as y equal to tangent inverse of x, which gives the angle y such that tangent of y equals x. And once again, we know the domain is all real numbers from negative infinity to infinity, and the range would be from negative pi over 2 to pi over 2. Let's go ahead and look at the tangent inverse function. So using decimals again, I'm going to go ahead and type in y equals to tangent inverse of x, and you can see it looks like this. I just want to point out that if we had tangent and y equal to tangent of x, we see that tangent has all these asymptotes, in particular between negative pi over 2, right? So if I just quickly do that, pi over 2 and x equal to negative pi over 2. Notice these, let me change the, make this black here, and then 1.5 dotted. And so right there, I'm going to get rid of the tangent function. Let's get rid of this for a moment. And so our inverse function, so we restricted it between negative pi over 2 to pi over 2. And so doing, let's restrict that there. So let's go ahead and do that. So negative pi over 2 to pi over 2. That's the portion that we restricted it to. Now notice these were vertical asymptotes, but when we graph tangent of inverse, these vertical asymptotes actually become horizontal asymptotes because of the restriction. So if you remove the tangent function, you can see that those vertical asymptotes become horizontal asymptotes. And, okay, so let's go back to the notes and continue that on. All right, so finding the exact values of tangent inverse of x, let theta equal to tangent inverse of x, rewrite theta equal to tangent inverse of x as tangent of theta equal to x, where negative pi over 2, sorry, theta falls between negative pi over 2 and pi over 2. Use the exact values in the table to find the value of theta in the interval pi over 2 to pi over 2, such that tangent of theta equals x. All right, so let's go ahead and evaluate tangent inverse of 1. So first we will let theta equal tangent inverse of 1. So that tells us if we rewrite this, we can rewrite this as tangent theta as 1, which tells us that we're looking for an output of tangent of 1. So there we go there. And we can see that it has corresponds to pi over 4. And so theta equals pi over 4. Therefore, tangent inverse of 1 equals pi over 4. All right, calculate tangent inverse of negative root 3. So similarly, we say theta, let theta equal tangent inverse of negative root 3, which tells us that tangent of theta is equal to negative root 3. And then using the table again here, we see we have a negative root 3, which is going to correspond to negative pi over 3. So that tells us theta is negative pi over 3 in return, which means tangent inverse of negative root 3 is negative pi over 3. All right, so that's how to find the exact values of tangent. Let's see some properties of, I like to call them the inverse properties for trigonometric functions. We see that sine well, before I even go over this, let's just remember that we have these compositions properties that f inverse, which is of x, which is the same thing as saying f of f inverse of x equals x, and f inverse of f at x, right? We could write that as f inverse of f of x is equal to x. So this is just the inverse properties. When two function inverses, you take the composition, you always get back what you input, right? And so whatever one function does, the other function just undoes it. And so we have those same properties here with sine inverse and so forth. So for instance, sine of sine inverse of x gives you just back x. And this is true for every x in the interval from -1 to 1. Likewise, sine inverse of sine of x equals x for every x in the interval from -pi/2. One thing to note is that sine of x, if you're treating it as having a domain of negative real numbers, this is not true. Okay, and so sine inverse of sine of x is x for only x in the interval from -pi/2 to pi/2. Likewise, cosine inverse has the same properties as well. Cosine of cosine inverse of x equals x for every x in the interval from -1 to 1. And then cosine inverse of cosine of x is equal to x for every x in the interval from 0 to pi. Tangent function and its inverse. So tangent of tangent inverse of x equals x for every real number x. Tangent inverse of tangent x equals x for every x in the interval from -pi/pi/2. All right, so let's go ahead and see how we could use these properties or not. Okay, and so for this next one here, we could see that we have cosine of cosine inverse, right? Find the exact value possible. So cosine of cosine inverse of 0.6. So this is simply just going to be 0.6, since 0.6 is in the interval from -1 to 1. Okay, and so it's just 0.6. However, sine inverse of sine of 3 pi/2 is not equal to 3 pi/2, since 3 pi/2 is not in the interval from -pi/2 to pi/2. And so for this one, we can actually figure out what the answer is still, but we just can't use that property that we just learned. So what is sine of 3 pi/2? Well, we know sine of 3 pi/2 because sine is defined for all real numbers. Okay, and so we know that value is just simply going to be -1. And then, so sine inverse of -1, then, well, once again, if we're trying to find that, well, theta is equal to sine inverse of -1, which means sine of this angle is -1, and we have to have theta in the interval between -pi/2 and pi/2. So the only choice for that would be theta equal to -pi/2. And so we see this is -pi/2. All right, well, cosine of cosine inverse of 1.5, well, 1.5 is not in the domain of cosine inverse, which would have been -1 to 1, and therefore cosine inverse of 1.5 is not defined or undefined. Okay. All right, so there's our answer for that one. Of course, this was the answer to this one, and of course, it's undefined. All right. Let's take a look at another example where we're finding the composite of two trig functions and an inverse function. So here we're actually finding the exact value of cosine tangent inverse of 5/12. And so what we're going to do is let theta equal 5/12, which tells us, and excuse me, not tangent, we're going to say let theta equal tangent inverse of 5 over 12. Okay, and so that would tell us, if we rewrite this is tangent of the angle, this is tangent of theta equal to 5 over 12. And we're going to use a right triangle to help us with this. We're going to say, okay, imagine we have a right triangle and we have the theta here. So by definition, tangent is opposite over adjacent. And so this would suggest this looks like 5 opposite over adjacent of 12. And so what is the hypotenuse here? Well, we know that the hypotenuse here squared would equal 12 squared plus 5 squared, which gives us 144 plus 25, which is 169. And so that means the hypotenuse would be the square root of 169, which is 13. And so we have this relationship of this triangle. So now if we have cosine of tangent inverse of 5 over 12, this is the same thing as saying cosine of this angle that we just from this triangle here. And so what is cosine? We know cosine is just adjacent over hypotenuse. And so if that's the case, then we have 12 over 13. And so we get 12 over 13. All right, let's try another example. An example that's very similar. Find the exact value of cotangent of sine inverse of negative 1/3. All right, so what we're going to do is say let theta equal negative 1/3, not negative 1/3, so keep on doing that, sine inverse of negative 1/3. All right, so that means that would say sine of theta is equal to negative 1/3. Instead of using a triangle, we can kind of think of this as the unit circle. So imagine you have a unit circle. Right, and so we know tangent, or excuse me, sine inverse is going to spit out an angle between negative pi over 2 to pi over 2. So it's going to be either this kind of direction or this kind of direction. So since it's negative, we know that this angle theta is going to have to reside somewhere over here in this angle. And that point there, if it's on the unit circle, has to have a y-coordinate of negative 1/3. So the point would be, has a coordinates x, negative 1/3. Now if this is the unit circle, we know that x squared plus y squared equals 1. And so substituting our y squared, we have negative 1/3 squared equal to 1. So we have x squared plus 1/9 equal to 1, which tells us x squared is 1 minus 1/9. So in other words, 1 minus 1/9, so 9 over 9 minus 1/9 would be 8 over 9. So take the square root of 8/9. And so we know, since it falls in quadrant 2, that our x coordinate is going to be positive. So this answer here would be the positive of it. And not only that, square root of 8 over 9 is the same thing as radical 2 times radical 2 over 3. And so now we know x is 2 root 2 over 3. Okay, so why does this help us here? Well, now we could figure out what cotangent of this angle is, because we have both coordinates on this point that corresponds to this circle, excuse me, this angle theta that's on the unit circle. So cotangent of this angle theta, or cotangent of sine inverse of negative 1/3, is the same thing as saying cotangent of this angle, where this angle intersects the unit circle at the point 2 root 2 3 comma negative 1/3. And so we know by the unit circle definition of cotangent, this is just x over y. So we're going to get 2 root 2 over 3 all over negative 1/3. And so we end up with a negative 2 root 2. Okay, so here we're asked to find an equivalent algebraic expression in x for sine of arc cosine of x on -1 less than or equal to x, x less than or equal to 1. And so an algebraic expression just means an expression just involving x, no sine or arc cosine here. And so what we'll do here is let theta equal arc cosine of x, and just remember arc cosine of x is the same thing as cosine inverse of x. All right, so this means that we could say cosine of theta is equal to x. And we're going to use a right triangle here to kind of help us figure this out. And so suppose we have a right triangle with an angle theta as one of its acute angles. And so cosine of this angle can be thought of as x over 1. And we know cosine is adjacent over hypotenuse, which tells us that we have x over 1. Now the missing other leg, or the length of the other side, has to be equal to 1 minus x squared. And you could show that using the Pythagorean theorem. In fact, we could also use, say, the definition of a unit circle to kind of get that same expression as well. Okay, so, but this helps us now, since we have the sides of this right triangle, to find an algebraic expression for sine of arc cosine of x. So that's the same thing as saying sine of that angle that we defined as theta. And using the right triangle, we know sine of theta is opposite over hypotenuse. So opposite in this triangle, opposite of this angle is that guy, and of course hypotenuse is that. And so what we have the square root of 1 minus x squared all over 1, which is just the square root of 1 minus x squared. Okay, and notice the restriction is between -1 and 1, because if we got something larger than that, that would be undefined. All right, next example here, we're asked to find the equivalent algebraic expression in x for tangent of arc sine of x on the interval from -1 to 1. All right, so let theta equal arc sine of x, which tells us sine of theta is equal to x. And once again, using a right triangle here to imagine this scenario. So here we have a right triangle, and one of its angles is theta. We know sine is opposite over hypotenuse, so that we could think of this x as x over 1. So then we would have opposite of this angle, which would be x, and hypotenuse of 1. All right, so then the other side would have to be 1 minus x squared. You could show that by using Pythagorean theorem. And now tangent of arc sine can be find an algebraic expression to replace this using this angle in right triangle. So then we could say tangent of this angle arc sine of x, which we call theta. So what is tangent of theta? Well, we know it's just opposite over adjacent. And what is opposite? Well, x. And then what is adjacent? The square root of 1 minus x squared. And there you go.